The MTU recording studio is used for the recording and mastering of countless audio projects. It should be a fairly dead space, with limited reverberation and reflections. There are many design considerations for the recording studio, and the space is continually progressing as a critical listening room. There has been ongoing improvement of the room acoustics in the MTU recording studio. The addition of several elements have greatly improved the sonic space: fiberglass above the drop ceiling panel absorbers in the four corners and the two side walls, a diaphragmatic bass absorber between the main output speakers. The fall 2008 semester was dedicated to evaluating and correcting the room to find where the remaining problems lie. The initial impulse will trail off without any more blips, but a reflection will result in a secondary impulse in the response. Testing was done with fuzz measure using the main studio speakers. The Earthworks M30 was used as the test microphone, which was connected to the audio laptop through an M-Audio Solo Firewire interface. The microphone was situated in several places, most notably directly behind the console, which is the main mixing position. The resonance of the room is analyzed through the frequency response of the space. The room showed considerable peaks at approximately 25.5 Hz and 51 Hz. The 25.5 Hz component is the fundamental frequency, and the 51 Hz frequency is a harmonic of the fundamental. The reverberation of 25.5 Hz and 51 Hz will contribute to a sloppy-sounding low end, which will create a muddiness in the mixed audio session. The goal is to design a solution that will tighten up the bass response of this room by minimizing the offending frequency. Think of it as notch filtering an entire room. The impulse response of the room displays a secondary impulse within the room at about 45.3 milliseconds, which makes the time difference between the impulses of about 9.5 milliseconds rounded. This extra impulse can be attributed to a reflection off one of the walls. Since the speed of sound is approximately 1000 feet/s, one can deduce the 1 foot 1 millisecond location of the reflection in the studio yields about a 9.5 feet round trip for the sound wave. This presumably puts it just above the existing wall panel opposite the entrance. Another panel absorber should cure this problem area in the studio. The primary focus of the semester was to correct the resonant frequency in the low end of the audio spectrum. The decision was to build a diaphragmatic absorber similar to the existing blocks placed between the speakers. A diaphragmatic absorber acts like a drum in the room. A solid box with 1x4 plywood used for the front and rear. The drum heads is constructed to allow a certain frequency to pass through. This frequency is trapped inside the absorber. The absorber resonates rather than the room, thus minimizing the undesirable frequency. Designing a diaphragmatic absorber is quite simple. There is no need for a frame, as it could make the heads more rigid, as well as overcomplicate things. While the diaphragmatic absorber was ultimately a success, the targeted frequency did not change the response of the room as much as had been planned. While there was a bit of attenuation of the 51 Hz component, at 2 decibels, there really was not much of a difference. The decay of that frequency did not decline very much at all, only about 5 milliseconds at most. This was the ultimate goal. The tests were not perfectly exact, as the many variables contributing to the variation between tests cannot all be controlled. One can assume these tests are accurate enough to make such observations. As far as the reverberation time is concerned, not much change was observed, as this was not really the main objective. The corner panels have addressed that problem quite well. Upon listening to music in the room, immediate results were not apparent. There was not a critical listening session before and after installation, so the casual listening involved cannot truly be reliable. Future testing will involve a series of recorded audio tracks. Each track will be played through the main output speakers, then recorded in the room. These tests will be completed without the bass absorber and with the bass absorber. While there is no substitute for listening in the room, a representation of what the microphone hears will be informative as to what the space really sounds like. These tests may not be as useful as the comparison of a room naked of absorption, then packed full of absorption. While the results of the semester's projects were somewhat successful, there is of course room for improvement. The intention of constructing the diaphragmatic bass absorber was the targeted attenuation of a specific frequency. This was achieved quite well, but there remains a band of frequencies surrounding the 51 Hz target that may still cause undesirable outcomes. The original thought was not to install acoustic material inside the absorber in order to target the 51 Hz component, but it may be beneficial to open the rear panel and install a bit of absorption. After all, there appears to be a small bandwidth around 50 Hz that still have peaks, and there is also a bit of a hump with a slow decay time at about 40 Hz as well. A sheet of fiberglass would widen the bandwidth of the absorber and may work well to tame those rogue frequencies. The addition of another wideband panel absorber on the wall opposite the door would eliminate the reflection seen on the initial impulse plot. There is a lot of reflective space above the location of the absorbers,